In late October 2003, while most of us were carving pumpkins for Halloween, the sun decided to throw a party of its own. A monster sunspot, a churning magnetic region on the solar surface more than 13 times wider than Earth, started to crackle with energy. And then it erupted. Over a 2-week period, it launched a series of solar storms at our planet. The most powerful of these was a flare so immense it overloaded the very satellites designed to measure it. Scientists later estimated it as an X-45 class explosion, the most powerful flare ever recorded. For several terrifying days, the barrage triggered a space weather event so violent it caused blackouts, disrupted satellites, and forced astronauts on the International Space Station to run for cover. But here's the truly scary part. The biggest blast didn't even hit us head-on. The chaos it caused was just a taste of what almost happened. The whole saga, now famously known as the Halloween solar storms, kicked off in mid-October 2003. A massive sunspot group, officially labeled Active Region 10486, swung into view, and scientists at NASA and NOAA knew it spelled trouble. It was one of the largest and most complex regions they'd seen in years, a coiled spring of solar energy just waiting to snap, and snap it did. On October 28th, it fired off a huge X-17 class flare. With it came a coronal mass ejection, or CME, a billion-ton cloud of magnetized gas, hurtling straight for Earth. This CME was incredibly fast, crossing the 93 million miles to our planet in just 19 hours, a trip that usually takes 2 or 3 days. When it slammed into our magnetic field, the effects were immediate. The resulting geomagnetic storm was rated G5, or extreme, the highest level possible. In southern Sweden, the power grid couldn't handle the strain. The city of Malmö was plunged into a blackout, leaving 50,000 people without power. In South Africa, a dozen transformers were permanently knocked out and had to be replaced, a surprising level of damage for a country so far from the poles. Up in the skies, things were even more serious. Airlines had to reroute flights away from the North Pole, where radiation levels were highest, to protect passengers and crew. GPS accuracy plummeted, disrupting navigation for everything from your car to military operations. For the astronauts aboard the International Space Station, the storm was a direct threat. As radiation alarms blared, they were ordered to shelter in the most heavily shielded section of the station. It was only the 3rd time in the station's history that they'd had to take such a drastic step. The storm also took a heavy toll on our satellites. Many experienced malfunctions or were forced into safe mode. The Japanese ADOS-2 satellite was lost completely, a total write-off. Even out at Mars, NASA's Odyssey orbiter wasn't safe. Its radiation instrument, designed to study this exact kind of phenomenon, was permanently fried by the storm. For days, our planet was under siege by its own star. And yet, this was just the beginning. So, what makes a solar storm so dangerous? It helps to remember that our sun isn't some peaceful ball of fire. Its surface is a chaotic mess of magnetic field lines, constantly twisting and tangling like cosmic spaghetti. Sometimes, they stretch so far, they snap and reconnect, releasing a mind-boggling amount of energy in a flash of light. That's a solar flare. Flares are graded like this. A is the weakest, followed by B, C, M, and then X-class, the Titans. The scale is logarithmic, so an X2 is twice as powerful as an X1. The Halloween storms produced multiple X-class flares, including the record-breaking monster that saturated satellite sensors. First measured as an X28, scientists later revised its strength to a staggering X45, the most powerful flare ever recorded by modern instruments. But the flare is just the opening act. The real heavyweight is the coronal mass ejection, or CME, that often comes with it. This is a colossal cloud of solar plasma and magnetic fields, weighing billions of tons, thrown into space at millions of miles per hour. It's this cloud that causes the biggest problems on Earth. If a CME is aimed our way, it smashes into our planet's magnetosphere, the natural magnetic shield protecting us. This impact is what triggers a geomagnetic storm. The collision energizes particles in our atmosphere, creating spectacular auroras. During the 2003 storms, the northern lights were seen as far south as Florida and Texas, a rare treat for people in those areas. But these storms also create powerful electrical currents in the ground, which can flow into any long conductor, like power lines or pipelines. These geomagnetically induced currents are what can overload transformers and bring down an entire electrical grid. In space, the flood of energetic particles can fry sensitive satellite electronics, degrade solar panels, and pose a serious radiation risk to astronauts. Now for the really unsettling part of the 2003 Halloween storms. That record-breaking X45 flare, which erupted on November 4th, wasn't actually aimed at us. The sunspot that created it had already rotated toward the edge of the sun. We only got a glancing blow. The flare itself was so intense that its X-rays overloaded the satellite detectors trying to measure it, forcing scientists to estimate its true power after the fact. The CME that followed tore through space, but the bulk of it sped right past Earth, missing us. All that chaos, the blackout in Sweden, the scrambled GPS, the endangered astronauts, was caused by the earlier, less powerful CMEs that scored a more direct hit. This raises the terrifying question that keeps space weather scientists up at night. What if that X45 blast had been aimed directly at us? What would the full, unrestrained fury of the most powerful solar storm ever recorded do to our planet? To understand those stakes, we need to look back in time, to an age before our modern world even existed. The year is 1859. On September 1st, an English astronomer named Richard Carrington is in his observatory sketching sunspots. Suddenly, he sees two patches of intensely bright and white light erupt. He has just become the first person to witness and record a solar flare. What he didn't know was that this was the opening act of the most powerful geomagnetic storm in recorded history. A little over 17 hours later, a massive CME slammed into Earth. The effects were stunning. The northern lights were so bright that people in the northeastern US could read newspapers by their glow. Gold miners in the Rocky Mountains woke up and started making breakfast, thinking it was dawn. Auroras were seen as far south as Cuba and Hawaii, but this was more than just a light show. The most advanced technology of the day, the telegraph system, went completely haywire. Telegraph lines sparked, shocking operators and setting paper on fire. Some systems were so supercharged by the storm that operators could disconnect their batteries and send messages using only the current from the aurora. The Carrington event, as it's now known, did little real damage in a world that ran on steam and muscle. But it set a terrifying benchmark. The Halloween storms of 2003 were a modern reminder of just how vulnerable our technology has become. The Carrington event showed us the sun's ultimate power. The Halloween storms proved that power is still very much active. So, what would happen if a Carrington-level storm, or a direct hit from an X-45 class event, happened today? It wouldn't just be a few telegraphs sparking, it could be a catastrophe on a global scale. The first and most severe impact would be on our power grids. The induced currents would surge through high-voltage transmission lines, overloading and literally melting the windings of giant transformers. These are the backbone of our electrical grids, and they aren't easily replaced. Manufacturing a new one can take months, sometimes years. A major storm could leave hundreds of millions of people without power, not for hours, but for weeks, months, or even longer. Without electricity, modern life grinds to a halt. Water supplies depend on electric pumps. Without them, taps run dry. Gas stations can't pump fuel. Grocery stores would be emptied in days, with no way to restock, because the entire supply chain is managed by systems that depend on electricity and digital logistics. In space, the damage would be devastating. A wave of radiation could wash over thousands of satellites, permanently disabling many of them. GPS would vanish. Global communications would falter. Financial markets, which rely on precision timing from GPS and global data networks, would be thrown into chaos. A 2013 study estimated that the cost of a similar event could reach up to $2.6 trillion in North America alone. It would be a cascading failure of nearly every system we rely on for daily life. The story of the Halloween storms isn't just a piece of history, it's a warning. These are the kinds of cosmic forces shaping our world every single day. If you want to keep exploring the powerful and sometimes frightening universe we live in, make sure you subscribe and hit that notification bell for more stories like this one. You might think an event like this is a once-in-a-millennium occurrence. You'd be wrong. In July 2012, a solar storm that many scientists believe was comparable in power to the 1859 Carrington event erupted from the sun. A massive CME tore through Earth's orbit. It missed us by just 9 days. If the eruption had happened 1 week earlier, our planet would have been directly in the line of fire. We got incredibly lucky. Scientists at NASA, NOAA, and agencies around the world monitor the sun 24/7. Satellites give us a constant eye on our star, allowing for warnings when a dangerous storm is on its way. But those warnings only give us a day or two of notice, enough time to protect some satellites and brace power grids, but not enough to prevent widespread disruption if the storm is big enough. The Halloween storms of 2003 were a warning shot. They were a stark reminder that we live in the atmosphere of a volatile star and that our modern tech-dependent world is incredibly fragile. The 2012 near miss proved the threat isn't hypothetical. It's a matter of when, not if. The real question is, will we be ready for the day the lights go out?